My guest today is Professor Peter Littlewood, who's professor of physics at the University of Chicago. His research activities include the dynamics of collective transport and phenomenology and microscopic theory of superconductors. Welcome, Peter.
Thank you. I'm very pleased to be here. Thank you, Gill.
Yeah, thanks for doing this. So I have some of your papers. Obviously, I don't understand them.
You're assuming that I do?
I hope to get a peripheral understanding of some of these topics, which seem really interesting. So I want to start with a paper entitled Non-Reciprocal Phase Transitions. And this is a paper that you wrote with a few of your Chicago colleagues from different departments, it looks like. That sort of highlights this area, and we talk more about this. This area is getting very multidisciplinary, it seems to me. So in this paper, you say, out of equilibrium, a lack of reciprocity is a rule rather than the exception. Non-reciprocity occurs, for instance, in active matter, non-equilibrium systems, networks of neurons, social groups with conformist and contrarian members, directional interface growth phenomena, and metamaterials. So I guess we need to get some definitions to sort of get into this. So first of all, what is lack of reciprocity? How do you define that?
Well, maybe we should define reciprocal, because as a physicist, this is something that you might be used to. And most of us think of it as Newton's third law. So Newton's third law says every force produces an equal and opposite reaction.
Yeah.
So I push on you, you push back on me. The force that we feel is the same. That's reciprocal. But systems which can think or do their own thing don't do this, right? So, so for example, if a fox chases after a chicken, the chicken doesn't push back on the fox. The chicken runs away. Right. So it really is
a smart chicken.
As simple as that, right? It is that, and so these are systems that have, we would say, non-reciprocal. If you looked at them just from the point of view of an object, say a fox is an object, a chicken is an object. What are the rules? Well, the rules are that indeed there's a non-reciprocal interaction. The force pushes on the chicken, and the chicken runs.
Chicken runs, yeah.
Right. So it's not surprising, and most of the world is like that. Right.
So biological systems.
So much of what we're thinking about in the end is biology, although not necessarily. We began by thinking about things like this with systems which are driven. Good example of something like that is a laser. Right. So again, a laser has an external source of energy coming into it, and an external output. So it's what, as a physicist, I would call an open system, and it means that that globally it doesn't satisfy the same rules. I mean, maybe microscopically it does, but if you look at it as an object, it behaves somehow oddly.
Yeah, so it's obviously counterintuitive. So you say Newton's third law doesn't quite work in some systems.
Right. Yeah.
But then it is because they are consuming energy at some level, right? So it is not violating the conservation of momentum or energy in any way, right?
Right. Exactly. So you're absolutely right. It means that, I mean, if think of it as a biological system, it's consuming energy, it's doing something. So of course, if I go microscopically into that biological system, all of the laws of physics still operate, right? But if I start looking at, an organism as an agent, as a thing, and ask what rules does it follow, I can simply prescribe it rules, very simplified rules to make models of these things. But then the rules will not be Newtonian mechanics. There'll be something else.
It won't be Newtonian mechanics, it will be something else, but we still have all the sort of the conservation principles there, right?
Well,
Well, that's
not
not
I
true.
mean, not
Yeah.
really, because I think, one would say that, um, in terms of the measurements that I can do, I can't tell that energy is conserved.
Mm.
So if I think of a bacterium sitting on a surface and moving around, you see it moves, right?
Yeah.
And it doesn't look like it's conserving energy,
Mm.
right? But that's because, if all you measure is its velocity,
Yeah.
you don't see that mv squared is conserved. Its energy isn't conserved. Its momentum isn't conserved.
Mm.
And of course, that that's okay because inside it's eating something. And
Yeah.
therefore, if I add together the chemicals that it's eating and the kinetic energy that it's doing, the sum of all of those things will be conserved.
Okay.
Right. So I'm not breaking any fundamental rules of the universe. But
Okay.
what I want is, I want a simpler description of that bacterium as an object
Yeah.
with a set of rules by which it operates. And I mean, people use this quite a lot. So sometimes this is called agent-based modeling.
Mm.
It's how people model crowds at football matches. They assume that that people can be treated as objects, and they have some interactions with the things around them, and they can be, you can make predictions about what they might do as a crowd.
Yeah. Yeah, so we want to talk deeply about the biological systems, but before we get there, I want to dig a little deeper into the sort of the physics of this. So you say here in this paper, we show that non-reciprocity leads to time-dependent phases in which spontaneously broken continuous symmetries are dynamically restored. So can you put that in
Yeah,
in a
in
fashion that
simple
I can
words, right?
understand?
Yeah, no, right. So
Yeah.
firstly, what do I mean? What does a physicist mean when they say phase transition? Well, many of these things are familiar. You're used to seeing the difference between water and ice,
Yeah.
and between water and steam, right?
Yeah.
And there's an abrupt change of state, that you go from something which is solid to something which is liquid to something which is a gas.
Right.
And we call those phases of matter. That's the name for them, because they have certain characteristics. Solids are actually solid. Liquids are not solid. And gases are much less dense.
Is that symmetry breaking?
Well, right. So okay, we'll come back to this. You've got a good
Okay.
one. So the
Yeah.
big one, which is symmetry breaking, is from solid to liquid.
Okay.
So in a solid, the atoms are all lined up. They're in a lattice. They're in an array.
Yeah.
If I know where one atom is, I know where all of the other atoms are, right? So they're in a periodic array. So that's a symmetry. Symmetry is and again, I can rotate it. It's a crystal. It has a shape. Okay, so all familiar things. So a liquid doesn't have that symmetry.
Yeah.
So a liquid is just featureless, really.
So the phase transition from liquid to gas, it's
right.
not symmetry breaking per se, because
That's right, exactly.
Okay.
So this we may come back to. You can sometimes have phase transitions which are abrupt, and don't have a symmetry breaking. Okay. And by the way, this enters into this story, so I'll tell you a little bit more about it. So normally, if I heat up water and I turn it to steam, there is an abrupt point where that happens, 100 degrees C, where the water is turned to steam, and it costs me some energy to get through that barrier. Okay. But actually, there's no symmetry difference between the liquid and the gas. And it turns out that I can, in fact, go continuously from a liquid to a gas if I'm prepared to change the pressure at which I do the experiment. So if you
back
go
again, I would imagine, right?
and back again. Right. So there are continuous paths.
Yeah.
And there's a discontinuous path. And there is an end point, which is called a critical point. Right. And so so that is one where there is there's still a phase transition, but there's no symmetry distinction. But anyway, I no.
Yeah.
And then probably I should move to, what about a non-reciprocal system?
Yeah.
Right. So the question then becomes, well, can it have phase transitions like conventional thermodynamic ones?
Mm-hmm.
Right. Now, this isn't obvious that it should. Right. So, and if I want to describe a phase transition between things with, one kind and another, I usually have to have some, we call it an order parameter, something I can measure that tells me that I'm in one phase rather than another. So coming back to solid and liquid, solids are solids. If I push on them, they have a restoring force, whereas if I push on a liquid, it just moves out of the way.
Mm.
Right. So there's a quantification of that I can here.
So is there sort of a natural state? I'm just thinking I have to heat up ice to get to water, so I have to add energy.
Yes.
So is there a natural state where materials want to be?
Well, it depends on it does depend on the temperature, right? So
yeah.
So there's if maybe the definition of the natural state would be, what would the state of the material be if I took temperature to 0?
Yeah.
Okay. That's and almost everything there will be a solid.
And if you take energy out, it will progress toward solid, right? Is that generally true?
By the way, the answer is not always.
Not always, okay.
Right, because there are a few very special things which are enormous scientific surprises that don't become solids, they in fact become superfluids or superconductors.
Okay, so
where the natural state of matter actually is a liquid rather than a solid.
Right. So people sort of get the solid to liquid to gas transitions. You say here we illustrate the mechanism with simple robotic demonstrations. So these are physical systems that we can go into to look at.
Yeah, right. So I think, so absolutely, right. So in fact, what we did was we made up, if you like, a game, and illustrated with robots, right? So we have these little robots, and actually, if you go to the web page of Nature, there's a video you can download which shows what happens, right? And so we program the robots to certain rules. So we have two kinds of robots: red robots and blue robots. Okay, and the robots. Well, we simplify things by not letting them drive around, but they can orient themselves. They can point in a direction, right? And we tell the red robots to all align with the other red robots. So not surprisingly, they all do that, right?
Yeah.
And we tell the blue robots to all align with the other blue robots.
Right.
And they also align. But then we give contradictory instructions to the red robots with the blue robots. We tell the red robots to align with the blue robots, and we tell the blue robots to anti-align, to align oppositely with the red robots.
Okay. Yeah.
Right. So there are so what can happen, and this depends on the strength of those instructions. But there are kind of two boring solutions.
Mm-hmm.
One boring solution is when when the aligners win over the anti-aligners. And so the red robots all align with the blue robots, and they just stay stationary and they don't move. Right? And then the other thing is if you change the strength of the instructions, where the anti-aligners win, and so then you find the red robots pointing one way and the blue robots pointing the other way. Right? So these are two static ordered phases. Okay, and by the way, if you think of these things as like little atoms, they look rather like models of magnetism, in fact. Well, no, the direction is the direction of magnetic moments, and I can make things that do this, right? So then you say, well, is that all there is, right? And then it turns out that in between those two phases, there's a boundary which again where they chase each other. Because what happens is that red and blue are a little bit anti-aligned.
Yeah.
And so blue is chasing and goes that way, and red goes the other way. Right? And they go round and round in circles. Okay? So so that's something that you couldn't have in a system with reciprocal interactions, with a thermodynamic system. You know, gases and liquids don't do this, at least not as far as we're aware.
So is it a lack of objective function for the system? You know, this sounds like U.S. elections, Peter.
Yeah, no. So by the way, I mean, I'm sorry to say that a lot of these models, right, you know, in principle, can have parallels in human societies. I say there are conformists and non-conformists, right? And indeed, you can produce dynamics where they chase each other. You can think about these things. I mean, you know, whether or not those models are the kind of models that I'm talking about are, you know, appropriate or accurate for all of these things. But of course, people do make more complicated models of human societies that do this. You know, I sometimes think of this as your modern version of Harry Seldon. If you ever read Isaac Asimov, right?
Yeah.
The Foundation trilogy. You know, this was the psychohistorian who had a theory of, you know, the interaction of people. And because there were so many people, you could put it into some statistical form and you could predict the future, right? So it's, I mean, say, no, we're taking very, very abstract views of processes which are, I think, you know, have some underlying connection. And I would say the one that I like best is neuroscience, and we may get to that in a moment.
Yeah, I'm really interested in that. So the instructions that you give to the robots here are localized. So it means that the system doesn't have an objective function, right? Only the
Correct.
localized agents.
Each robot is trying to do its own thing with its own set of rules. It looks at its neighbors, right, to decide to do this. So, by the way, you know, there are not uncommon situations which you might be familiar with where one sees this kind of thing. Bird flocks. If you look at flocks of starlings, right?
Yeah.
No, they flock and they fly together, right? And so is it because they've got some global orientation system that tells them to fly in a particular direction? No, not at all. It's the fact that each bird is, you know, looking around at a few of its neighbors and decides to orient itself with the neighbors. And then that builds up and produces a pattern where all of the whole flock is moving in a concerted system.
So the beauty of this is that a simple objective function given to the agents ultimately get to a very complex system behavior, right? In some ways, is that the way to think about it?
That's exactly the way to think about it, because they say that and so, you know, that's, you know, it's a kind of a bottom-up production of structure, right?
And you go a little bit into, so you say here we describe the emergence of these phases using insights from bifurcation theory and non-Hermitian quantum mechanics. Do we have some applications here in quantum mechanics?
Yeah, we do actually. So I will say that before this paper, the way I got involved with this was actually by thinking about models of lasers.
Yeah.
Okay. So these are quantum mechanical systems, but they're similar in the sense that what happens in them, of course, is that they develop some spontaneous coherence, right? Laser light comes out, it's at a single frequency, it's completely phase coherent. So how does it do that? Well, it does that because of spontaneous cooperation between lots of atoms interacting via photons. Okay. So of course, we've known about lasers for a very long time. But you know, one of the things that we discovered is that you can change the parameters of lasers to go through something like a liquid to gas transition. So there are kinds of lasers where, if you like, the systems are very cold. The photons are really behaving like bosons, and you have something which is producing what I would call a Bose condensate. So they're all in a macroscopic superposition, the same state. And there's another limit where, which is much higher temperature typically, where, and the regular laser that you have in your laser pointer, where the photons become highly coherent, but the things that they're living with don't, and it's a very much denser regime. But I mean, they're dynamical phases in the sense that I have to give them energy. I pump them and things leave.
Yeah.
And so the models you make for them actually have this characteristic that they have dissipation, which quantum mechanics doesn't have.
Does it have any implications for quantum entanglement in any way?
Yeah, I mean, many of these things do, because one of the, I mean, we're doing a very specific thing about talking about macroscopic systems composed of many agents. Mostly when people are talking about quantum entanglement, you're talking about small systems of a few photons. But if you scale them up, actually, what the transitions that we're looking for are very much associated with changing the correlation functions, so-called quantum entanglement of photons in these systems. And so people are now beginning to build models of these so-called polariton condensates that they're hoping to build quantum computers with and things like this, right? So, I mean, that's not quite my space. I mean, so I'm trying to think about, some of these fundamental things, because, again, one of the things we discovered really is that in those systems, as well as having the system in the liquid phase or in the gas phase, there is this version of cycling between two different systems periodically in time. Right?
Yeah.
So it's a system which half the time thinks it's a liquid, half the time thinks it's a gas, and is oscillating periodically between those two things. I mean, that seems like a crazy thing to do. And and it turns out that these things are seen and you can make them. What we can use them for, I have no idea.
Yeah.
Right.
Yeah, I mean, without knowing anything about it, synchronization of macro systems seems to be sort of in the same area of quantum entanglement. It is sort of the ultimate synchronization between two particles.
No, I mean, well, it is. I mean, I say that I mean, however, you should say that when things get synchronized, they actually become very unquantum.
Yeah.
Because everything is moving together. There's just one object, right? There's no information left there.
Right.
So oddly, sort of things like superconductors and superfluids and lasers and things like this, you think of as manifestations of truly quantum physics, which they are, but the state you end up with is more analogous to a brick. It's
yeah, that's so interesting. So I think this is related, Peter. So I have another paper, recent paper, non-reciprocal frustration meets geometrical frustration. You say here, new theoretical work establishes an analogy between systems that are dynamically frustrated, such as glasses, and thermodynamic systems whose members have conflicting goals, such as predator-prey ecosystems. And so I know that glasses are quite an interesting thing to study, isn't it? So what's happening there?
Yeah. Well, no. So I mean, so this was actually, I mean, this was me commenting, in fact, on a paper by one of the co-authors of our original thing. So this is Ryo Hanai's paper, and he was my postdoc here in Chicago. He's now got a faculty position in Japan. He's doing very well, and he wrote this very interesting paper that I wanted to comment on. So, okay, so what's a glass? Okay. And so, I mean, you're used to window glass.
Yeah.
This is a system that is a solid but looks like a liquid.
Right.
So these are very strange things, really. I don't think one would have ever predicted that they exist. Okay. But they're familiar to us because we see them. and they've provoked a huge amount of theoretical effort over decades to try and resolve them. Some of which ended up actually in a Nobel Prize a couple of years ago for Giorgio Parisi, who famously proposed a very simple model for this. And so, so one of the things that that happens in Parisi's model, and probably is quite close to what happens in reality, is why do you get a glass? Well, it's actually because the system can't decide where to sit. There are many possible configurations of where things could be. And each of them are equally good.
Equally good from a sort of energy minimization perspective?
Yeah, equally good from an energy minimization point of view. They may not be the absolute ground state. The absolute ground state is probably a crystal, right?
Yeah.
Right? But they're all equally good. And they're very far apart in the sense that you can't deform from one into the other smoothly. Because if you could, you'd have a liquid.
Right.
They're just a configuration of atoms, and I've got a frozen configuration here and another frozen configuration over there, and they're completely different, and I can't smoothly go from one into the other. And in fact, the barriers between them are thermodynamically very large.
Yeah.
So we call these systems frustrated.
Yeah.
Right? I mean, because
that's a good term
right,
for it. Yeah.
That's right. So but it's an energetic frustration. There's a Hamiltonian. It's just that the system can't find its way, and each time you cool it, if you take the same system and you cool it down again and again and again and again, each time it ends up somewhat different.
Okay.
Good, right. So then, the system that Rio was studying is basically one of these so-called dynamical systems that very similar to the ones that we were talking about. And he builds a model which is maximally frustrated. Right? And
okay.
so what does that mean? In my language, it means that the forces are completely anti-symmetric. So I say I push on something, it runs away. I can quantify that by some number, some interaction strength, and the one chasing is positive and the one running away is negative, and I make them identically opposite.
It is still a minimum energy state still.
Well, it won't be. So again, there's no clear definition of energy here.
Okay. Because
all I have equations of motion. So I say I have, if you like, Newton's laws, but I don't have the third one. So I can give the system these equations and I can follow them and they'll produce things and they'll run around. And it may reach a steady state. Right. But the steady state is not a minimum of energy.
Okay.
I have difficulty defining what an energy is. I mean, I could define it in various ways, but it's not. It's a principle. So then but then you say, how do I characterize systems like this? Right. So what you do is you characterize it by saying, well, suppose I go in there, it's moving around, and I'll now ask, what happens if I perturb the system a little bit? I push it. Okay. And so normally when I push something which has an energy, it rolls back to where I started. So I push it out of equilibrium, it rolls back. Now that can happen in one of these dynamical systems too, is that it prefers to be flowing in this way. So if I divert it and push it a little bit to the side, it comes back.
Yeah.
Right? So the rate at which it comes back, it's sort of a time constant. Some things will come back slowly, some things will come back very fast. That has a name. It's called a Lyapunov exponent. It's the time taken to come back. Right. And of course, if I've got a big system, there are many possible ways I can push it. I can push it up, I can push it down, I can push it in, many, many dimensions. And so I will have a whole host of those time constants by which it comes back. So it turns out actually that in this particular system, these time constants are generically all infinite,
Hmm.
which means that the system is infinitely malleable.
Yeah.
You can push it anyway, and it's automatically happy to do this.
It could be a different state, but it's still happy there in the new state.
Well, it's still happy in the new state because the new state is exactly the same as the old state.
Right.
So this is the analogy to a glass, right?
Yeah.
I've got a state here which is a minimum of energy. I've got another one which is different, but it has exactly the same energy minimum. And therefore, there's no reason ever to fluctuate from one to the other because there's no thermodynamic penalty. And so here the analogy is exactly that the system can do this, can move around.
Yeah, so there's no optimization needed in some sense. So you can go from X to X prime and to X double prime, and they're all equivalent
very
states,
smoothly
yeah.
by changing parameters, right?
So you say here, Peter, that a dynamical system might settle down to a time stationary fixed point in phase space, where all the relevant variables become constant. What is the intuition behind that?
Oh no, sorry, that was me arguing with the editor who wanted a very precise definition of a stationary state. It's a solid.
Okay.
Right, exactly. It's,
yeah. So I want to spend some time on your third paper, which is really, really interesting. I always struggled with connecting physics to biology.
yeah.
Not that I know physics or biology, for that matter. So you have a paper here, The Mind of a Mouse.
Yep.
And you say here large scientific projects in genomics and astronomy are influential, not because they answer any single question, but because they enable investigation of continuously arising new questions from the same data-rich sources. Advances in automated mapping of the brain's synaptic connections, connectomics, they're called, suggest that the complicated circuits underlying brain function are ripe for analysis. We discussed benefits of mapping a mouse brain at the level of synapses. Um, so we have this big thing going on called artificial intelligence. I always felt that we are sort of on the wrong track there. Because most of the things are what we call supervised machine learning. And I think you talk about this in this paper that needs millions of labeled data. If I show a computer a million cats and a million dogs, at some point it says it's again this dog. It's an interesting statistical problem, but nothing to do with intelligence anyway, I would argue.
Yeah.
And so, but here there's sort of a different direction, right? If you try to combine what we learn from physics into thinking about the brain, I don't know if you ever get to sort of mapping the human brain, but you say here if you map a mouse brain, which in itself is such a complex task, I don't know how long it's going to take, that might give us some insights, right?
Well, we hope so. I mean, so firstly, you should see them. This is a paper with lots of authors, and it's kind of a manifesto. And part of the idea of this is that if a lot of important people, not necessarily me, but many other important authors on this list, vote for this, maybe the federal government will spend some money to do it, right? And so firstly, what we recognize is that the technology has got to the point where it should now be possible to do this. And it's always odd to me, for example, talking to neuroscientists. Neuroscientists make up all kinds of theories about neuroscience without actually knowing how the brain is wired up.
Yes.
As a physicist, if I didn't know, what the bits are inside, I wouldn't even start to look at a problem, right? So I just wouldn't know how to start, right? So the first idea here in this is that the simplest thing that one should get is actually a map of all of the connections in the brain.
Yeah.
And by the way, we now have one for the fly. So the fly brain has now been mapped.
Yeah.
Right.
But and how many neurons are there in a fly?
I forget. I mean, it's some. I can tell. I mean, so in the fly brain, I think it's maybe a few 100,000.
Oh, a few 100,000. Okay.
Yeah. Right. So I mean, if you're talking about, of course, mammalian brains, you're scaling up to numbers which are kind of ridiculously large.
Yeah, I think 10 to 10 or 10 to 11.
10 to the 10, 10 to the 11 is the kind of number, right? And probably each neuron has about 1,000 connections to other neurons, right?
Yeah.
But nonetheless, this is a problem which I think will get solved in the next 5 to 10 years. We will do this probably first on the mouse and then beginning to do this with humans. Um, so the pitch in that thing was, of course, that what could this be good for, right? Well, we hope it would be transformative in the same way that mapping the DNA has provided a database for to be able to do vast numbers of things in biology and medicine, right? But it depended first and foremost on actually sequencing all the DNA.
Mm-hmm.
And now we do that routinely. We can sequence everybody's DNA. We can do it quickly. We do all of that, and it becomes a basis for how we think about biology entirely. And our view, I think, is that if you have, the map, that again provides the substrate on which you think about all of the dynamics. Right. And then, I will come back actually to the first point about the first paper we talked about, which is that, one of the best examples of non-reciprocal dynamical systems are neurons.
Yeah.
You have two kinds of neurons in your brain. There are neurons which are excitatory and neurons which are inhibitory. So excitatory neurons make the next one fire. They have a positive interaction. Inhibitory neurons prevent the next neuron from firing. They're right. And as a result of the existence of both excitatory and inhibitory neurons, your brain is naturally active.
Yeah.
It produces circuits and cycles and things like this. Okay. So the kinds of circuit, and that's what we think of as brain activity. Brain activity is, in fact, some kind of partially synchronized actions from one to the other. And the way that we recognize objects is by dealing with those synchronies, not the way that AI does. In AI, AI is basically making a model of a spin glass. Many of the AI models are, based at least in concept on ideas from statistical physics of the kind of things that I was talking to with glasses, right? There's a minimum here, that's a dog. There's a minimum here, that's a cat. And then there are classes of minima that are nearby a species of dogs, and they're far away from cats.
Yeah, I mean, I just, I don't know if I'm thinking about this correctly, Peter. So suppose I'm an extraterrestrial, just came here, and I get fascinated by computers.
Right.
And I say, I'm going to take the Intel microprocessor out of it, and I'm going to have fine slices of it to really understand how the computer works. But I would never understand how the software or the operating system work, right? I mean, yeah. So
no, right, no, absolutely. So I mean, I think well, in fact, this is something of a sort of a running conversation actually in science community to say, well, suppose I were to do connectomics on a microprocessor, would it help? And the answer is, of course, it wouldn't really, because I mean, after I've looked at all of these things, could I feed it into some artificial neural network and decide how it worked? Probably not, right?
Yeah.
Okay, right. So, I'm betting that brains are much simpler.
Okay.
Right. That I mean, so that there are, and I think most people would believe this, that there are very simple principles on which neural circuits work, right? That they're adaptable because they have to be influenced by the environment, they have to be influenced by the task, they're slightly different in the retina than in somewhere else, and but fundamentally the same kind of rules of play, and you just speciate it, right? Right. But nonetheless, there are kind of well-defined circuits doing well-defined things. And now we've learned this, by the way, in the fly.
Yeah.
So it turns out that in the fly, as distinct from what you could do with a microchip, you can find specific circuits in the fly brain that do specific things. And you can actually map them to function.
Yes, the software is sort of embedded in the hardware.
The software is actually embedded in the structure, which is the natural way to do this, right? And remember that the reason that brains are remarkably efficient and energy-wise, because you don't program them from the outside, right? You don't have to provide a power source from the outside, right? You don't have to plug it into a battery, right? You just feed it and it's eating, right? Right, and your brain operates on 20 or 30 watts,
right?
Whereas which is remarkably low power, at Argonne, and I think we're about to install a sort of next generation supercomputer, which I think is going to be 10 megawatts or so. So it's enough power to run a small town, and it's probably not as smart as a small dog.
Right? Yeah. So if I understand this correctly, Peter, your hypothesis is that two things. I think if I understand this correctly, one is the brain is very different from a computer. And we just started to try to understand it, and to get the hardware map of the brain could be useful. I mean, it may not be the answer, but it could be useful starting point, right? Sure,
right. And there are all kinds of ways that one can gradually begin to approach that with small scale things. So, you can try and design small neural circuits, and you can build them in vitro.
Yeah. So one thing I was wondering about is, if I pick one fly and sort of do this on that fly, there are a lot of complications there, right? So the fly is evolving from some set of initial conditions, and it is using its experiences to get to time equal to 0. What we learned from that, I think you're arguing that it's not substantially different from any other fly. Do we have any data on that?
We don't really know. We have to do the second fly.
Yes.
Right. But I mean, I will say that there is a belief actually that insects are quite programmed in development. That there are very stereotypical circuits which will be there in all of them, and they may differ in detail, but they won't be very different, right? So if you come to vertebrates and mammals, there's obviously a lot more plasticity.
Yeah.
We simply know. I mean, there are people who are born with only half a brain and discover it late in life. They were perfectly functional.
Right.
But it is also true, for example, and this is, I think, one of the things that we'll learn when we start doing connectomics properly, that there are diseases of the brain that are structural. We know a lot about diseases of the brain that are chemical.
Yeah.
We have lots of drugs to treat various kinds of things, but there are probably...
They don't typically work, but we do have a lot of chemicals.
We have those drugs, but we think you do change the brain's chemistry, right? It may well be that there are some diseases which are really associated with the architecture of the brain not working, right? I mean, and there are some real hypotheses that diseases like schizophrenia may be of this kind, right? So long before we'll learn about the complete architecture of a whole brain, we'll begin to learn about the differences, either associated with development or with disease or others that will give you a different kind of insight. Yes.
Yeah, let me know if I'm thinking about this correctly, Peter. So we have moved from sort of a network to centralization again. We have these big clouds, Amazon, Microsoft, and so on. And the latest trend is moving back into what's called edge computing. So Internet of Things, they're sort of doing processing on site
Yeah.
type model. Would you say the brain is closer to that than centralization? I mean, there is no central
No,
processing unit in
there's,
the brain,
there's,
right?
right. So there is no CPU. So I mean, so indeed, I mean, the reason that, as you say, that edge computing happens is that our ability to collect data has grown faster than our ability to compute with it. So you see this in science very commonly. You build these enormous telescopes and they're taking vast amounts of data, but you can't store the data and analyze it later.
Right.
You actually have to analyze the data as you take the data, right?
Right.
And this is happening indeed in the computing world all the time, because we're sort of data driven. And I mean, you've probably seen these plots that show, the rate at which data is being produced growing much faster than the data rate at which compute is being produced. So you do this. But the brain is an object that has to do that par excellence, because you're using data to make a decision in real time, right?
Yeah.
If you don't spot the tiger, you're dead, right? So it's just
Right. Yeah. That's what I was thinking, Peter. So there's a difference between the prey and the predator. The prey has a much higher need of real-time processing to survive. The predator, I'm just making a
I don't
speculation
know.
here.
Yeah,
The predator less so. So if you look at the pyramid of biological systems, the one sitting on top has less of a need for real-time processing, would you say?
Well, I
I'm
mean,
just
it's sort of
asking a question
interesting
here.
thought. I mean, I don't know. I mean, I think that actually, uh, no, you know, catching something and biting its head off is not easy,
Yeah.
right? So um, often actually the prey can have a much more stereotypical response. So
Yeah.
certainly flocks do, right? So the answer is there are a flock of birds. There's an eagle. There's one eagle. There's many birds. Chances are the eagle will eventually get one of the birds.
Right.
But the strategy for the flock has to be to make sure that it doesn't do it very often. Right.
The strategy for the
So,
flow.
right, so actually, in that case, the flocking behavior and the dissolution of the flock and things you see in fish schooling and things like that are quite stereotypical, whereas the tuna has to think harder, because it has to deal with it's having chaff thrown at it. It has to make decisions. So I think I'd go the other way around on that one. But I hadn't really thought about this. I mean,
Yeah.
uh,
No. Yeah, I'm thinking now we have this Internet of Things, IoT
yeah, right.
Devices. And if you consider that as a system, I haven't thought about this much, Peter. I'm just sort of speculating. A more efficient system would be something that communicates with its neighbors in some systematic way, rather than trying to do a computation and make a decision
Yeah.
individually, right? Yeah.
Yeah, well, I mean, I don't know very much about this, but certainly those models are there. Um, so I mean, in many cities these days, there are lots of sensors distributed around.
Yeah.
Producing data, trying to send it in, right? And those sensor networks kind of communicate in arrays, but they don't think about everybody else's data. They decide what they're going to do based on things that they know locally.
Yeah.
And then there may be something that scoops up all of the data centrally to try and do that. But indeed, we are trying to build active networks that do that, because it's the most efficient way, power-wise. You don't want to provide an expensive high-power chip associated with every streetlight.
Yeah, it's interesting. Autonomous driving has taken some some issues lately, but it almost intuitively feels like a city of a large number of autonomous modalities will do better than a few.
It should.
And then we see that in aircrafts, right? Aircrafts are sort of autonomous driving vehicles, and all airplanes in the air are equipped with autonomous driving, and they do seems to do a lot better than cars.
Yeah, I don't know why, but firstly, I guess in general, the environment that an aircraft is in is a lot more predictable.
Yeah.
Right.
We also have
people,
a second dimension.
there's right. There's another dimension to flight, right? So that the right. But I think one of the difficulties with autonomous vehicles, I am told, is the massive amount of computation that you have to do on that vehicle to deal with the range of environments that you're in. And the goal, frankly, is to push that away from the vehicle into the city. I think that was your intuition, right?
Or some other vehicle that's sitting,
or some other vehicle that's sitting nearby, right?
Yeah.
So that so you do some local communication with that, and therefore you learn, and you don't have to, match against some vast data set of these things. Because part of the problem is, particularly when you've got systems which have been trained on these things, you train in particular environments, and someday you're driving along and you'll meet a tank. Right,
Yeah.
That's not in the training set. So what do you do? There may be a sort of different solutions to these. Right.
Yeah, it seems like, going back to the brain, it seems like in some ways the brain is doing that, right? It appears very collaborative that,
right.
If something is sort of failing in one area, it can sort of push that data to somewhere else, get it processed. As you said, somebody losing half his or her brain still function because other parts sort of specialize in things that have been lost. So brain is sort of a natural device that appears to be highly collaborative in the AI space. We haven't built anything like that yet. I don't think
so. Maybe some of the AI people are doing so, but the point is that the massive AI models that people are building are built around very monolithic architectures.
Yeah.
Right. That are that are working in a very different space. Now, of course, people are working hard to simplify them. They're also working hard to try and understand why they work.
Yeah.
Right. Okay. And one of the things, by the way, that seems to be key to some of the latest best algorithms is that they have this malleability that I was referring to you in this paper by Rio Hanai.
Yeah.
Where actually the point is, if you're analyzing a dog, there's a whole class of dogs, and you can continuously transform from one dog to the other. There's not a minimum around one dog and another minimum around another dog, so it's very brittle to decide where you're going between those two.
Right.
So this ability to build in some malleability is something which seems to have come out of those models, but without anybody really understanding why it's there. I would say the scary thing I find about AI is that we really don't know why it works.
Yes, yeah, I think that's fair. Do you see any applications directly into AI from what we talked about, in terms of the frustration you talked about in non-reciprocal systems?
Well, potentially, but I say it's a rather abstract influence.
Yeah.
Right. But the first thing I'm saying is I think that one should actually think of brains as a dynamical system and not as something which is minimizing something. That's a change in philosophy.
Yeah.
Right. So, and there are plenty of people thinking that way. But there's nobody building architectures like that because it doesn't fit for a digital world. It would fit only into a world which had a very different form of computing underlying it.
Right.
So,
or we just have to maybe invent a new sort of computing architecture.
People call it neuromorphic computing. I don't think anybody knows what it. I don't think anybody knows what it really is. But it would be.
Yeah.
Right. Well, look, there's another way to think of a brain actually, which is to realize that it's really a smart battery.
Yeah.
It's a power source. Fundamentally, what you do is you maintain a chemical potential difference between the inside of the cell and the outside of the cell. You're doing that by feeding something. It's an electrochemical potential, just like in a battery. Okay.
So maybe we have to create computers that are electrochemical magnetic, in its
Yeah, I
process.
have colleagues who are trying. Right, and again, you know,
Yeah.
I don't think any of us believe that these things will, you know, necessarily be practical anytime soon.
Yeah.
But we think that trying to understand and establish the principles could be very valuable.
Absolutely.
So,
Excellent. Yeah, this has been great, Peter. I learned some stuff.
well, no. Thank you. You asked very good questions. I mean, so I'm intrigued, by the way, why you choose to run a science podcast.
So I started, along with COVID, where I couldn't travel anywhere. I thought it'd be interesting to talk to people of, various ideas and disciplines. And I think the general public gains something from it. I mean, there is always new information coming out. I don't know if the general public, I don't have a very large following, but
No,
yeah.
no, no. Obviously, there are definitely people who are listening to you, and so yeah. So I hope I wasn't too abstract and obscure.
Excellent. Yeah, yeah. I think we made it approachable.
Good,
Thank
indeed.
you.
So
Yeah,
I'll
thanks
look
for
for some
spending
of
time
your
with me.
stuff in the future anyway. So thank you very much.
Thank you.
Bye now.